Okay, let's start with, well, probably the most iconic fruit in science history, the apple.
Right, the classic image, Newton under the tree.
Exactly. We all picture him seeing it fall straight down. But the real puzzle, the thing that really stumped people back then, it wasn't that it fell.
No, not at all. Apples fall, that's normal. The big mystery was actually the moon.
Ah, right. If the Earth pulls the apple down, surely it's pulling the moon, too.
Precisely. So why doesn't the moon just, come crashing down onto us? Why does it stay up there, just circling around? It seemed like a huge contradiction.
And that contradiction, that moment, Newton apparently connected the everyday apple to the moon's path. That's basically the birth of modern physics, isn't it?
It really is. So this deep dive, it's our way into understanding two fundamental ideas. First, the force that governs the whole universe.
Gravitation.
Yes. And second, how we experience forces right here, specifically in fluids. That takes us from Newton all the way back to Archimedes.
We're covering Newton's cosmos and Archimedes' bathtub discovery. Sounds good.
Let's get into it.
Okay, let's unpack this. So, back under that legendary apple tree, Newton's big idea was basically if gravity works here on the ground and even reaches the top of mountains.
Why shouldn't it reach all the way to the moon? It had to be the same force. The pull on the apple, the pull on the moon, same thing.
Okay, but then we're back to the question. If Earth is constantly pulling the moon, why no collision? How does it stay up?
Well, that's where the physics of moving in a circle comes in. It's actually quite neat.
Right, like, if you swing a stone on a string around your head.
Exactly like that. Think about it. You're constantly pulling the stone inwards with the string, right?
Yeah, towards my hand in the middle.
That inward force is what we call the centripetal force, center seeking. And because you're constantly changing the stone's direction, even if the speed is steady, it's accelerating.
Okay, acceleration isn't just speeding up, it's changing direction too.
Got it. And what happens if you suddenly let go of the string?
The stone flies off straight out, like tangential to the circle it was making.
Perfect. It flies off in a straight line. That's its natural motion without that inward force.
So connecting this back to the moon, Earth's gravity is like the string.
Exactly. Gravity provides that constant inward centripetal pull. The moon has this immense forward velocity, wanting to shoot off in a straight line into space.
It's inertia, right.
Yes, it's inertia. But Earth's gravity continuously pulls it inwards, bending its path into an orbit.
So let me check if I've got this. The moon is falling towards Earth constantly,
Hmm.
but it's moving sideways so fast that it just keeps missing.
That's a great way to put it. Precisely. It's falling around Earth, not into it.
Yeah.
And realizing that gravity was this universal thing, acting both here and out there, that's what let Newton crack the code of the cosmos.
Which brings us neatly to his universal law of gravitation. This was the really big leap, wasn't it? Saying that every object pulls on every other object.
Yes, everything. From tiny dust motes to giant stars, you, me, the planets, everything attracts everything else. It's universal.
And he didn't just say that. He worked out the rules, the maths behind it.
He did. And the rules are actually quite elegant. First part. The strength of the attraction, the force, is directly proportional to how massive the objects are.
So bigger mass means stronger pull.
Simple as that.
Yeah.
Multiply their masses together. The bigger the product, the bigger the force.
Okay, that makes sense. What's the second part? That's the distance one, right? The inverse square thing.
That's the one. And it's crucial. The force is inversely proportional to the square of the distance between the centers of the two objects.
Inverse square. Okay,
Yeah.
what does that mean in, like, practical terms?
It means the force gets weaker really, really fast as things get further apart. Let's use the example from our source. Imagine you have two objects, and you move them so they're 6 times further apart than they were.
Okay, 6 times the distance.
The force between them doesn't just become 1/6. It becomes 1/6 squared.
1 over 36? Wow, okay.
Oh.
So the pull drops off dramatically.
Extremely dramatically. That inverse square relationship is why, even though Jupiter's massive, its gravitational pull on us here is minuscule compared to Earth's.
Right.
It's just too far away.
Right, but hang on, there's something that feels a bit weird here. If every object pulls on every other object, when an apple falls, shouldn't the Earth technically move up towards the apple too?
Ah, good question. According to Newton's third law for every action, there's an equal and opposite reaction.
Mhm.
You're absolutely right. The apple pulls on the Earth with the exact same force that the Earth pulls on the apple.
We definitely don't see the Earth leap up to meet the apple, so what gives?
The key is Newton's second law. Force equals mass times acceleration, F1.
Okay.
If the force F is the same for both the Earth and the apple, then the acceleration A must be inversely proportional to the mass, m. You can rearrange it to Fm.
Ah, so the force is the same, but the Earth's mass is gigantic compared to the apple's tiny mass.
Exactly. So divide the same force by the Earth's enormous mass, and the resulting acceleration of the Earth is, well, incredibly, unbelievably tiny, completely negligible.
So it does move, theoretically, but just by an amount so small we could never possibly notice it.
Pretty much. For all practical purposes, only the apple seems to accelerate significantly. And the beauty of this whole law is how it tied everything together.
Like what specifically?
Well, think about it. It explained why we're stuck to the Earth, 2, the moon's orbit, 3, the planets orbiting the sun, and even 4, the ocean tides, which are caused by the moon and sun's gravity. 4 totally different seeming things, all explained by one universal law. It was revolutionary.
Truly foundational stuff. Okay, so that's the grand scale. Let's bring it back down to Earth, literally. When something falls just under gravity's influence, that's free fall, right?
Yes, free fall is when gravity is the only significant force acting on a falling object.
And since it speeds up as it falls, its velocity changes, meaning it's accelerating.
Correct. And we give that specific acceleration caused by Earth's gravity a special name, g.
No, there's a famous story about Galileo, isn't there? About dropping things off the Leaning Tower of Pisa.
Ah, yes. The idea he was testing was fascinating. That the acceleration due to gravity, g, is actually the same for all objects, regardless of how heavy they are.
So a feather and a cannonball should fall at the same rate.
According to the principle, yes. He supposedly dropped different weights from the tower to show they land together.
But wait a minute. If I drop, say, a crumpled ball of paper and a rock right now, the rock definitely hits the floor first. We see that all the time.
And that's the crucial real-world difference. Air resistance.
Friction from the air.
Exactly. Air pushes back against falling objects. For a light, spread-out object like a piece of paper, or even a feather, the air resistance is significant compared to its weight. It slows it down a lot. The dense rock cuts through the air much more easily.
So Galileo's principle only really works if there's no air.
Precisely. If you do the experiment in a vacuum, pump all the air out of a chamber, then a feather and a hammer dropped together do hit the bottom at the exact same instant. Astronauts actually did this on the moon, where there's no atmosphere. Gravity pulls equally on mass, friction doesn't.
Okay, that makes sense. And this whole discussion, it leads right into the difference between mass and weight, doesn't it? People mix those up all the time.
They really do, but they're fundamentally different concepts in physics. Mass, usually written as m, is basically the amount of stuff in an object. It's a measure of its inertia, how resistant it is to changes in motion.
And mass stays the same no matter where you are.
Correct. Your mass is constant on Earth, on the moon, floating in deep space. It's an intrinsic property.
But weight. Weight is different.
Weight is a force. Specifically, it's the force of gravitational attraction exerted on an object by a large body, like a planet or moon. We calculate it as weight equals mass, m times the acceleration due to gravity, g. So W is mg.
Uh-huh. So since weight depends on g, and g can be different depending on where you are.
Your weight changes. It's location dependent. G depends on the mass and size of the planet or moon you're on. You'd weigh a lot more on Jupiter and a lot less on Mars, even though your mass hasn't changed one bit.
And the classic example is the moon, right? Because it's smaller and less massive than Earth.
Exactly. The moon's gravity is weaker. G on the moon is much less than G on Earth.
Okay.
So an object's weight on the moon is only about 1/6 of its weight here on Earth.
So if something weighs, say, 10 newtons here.
On the moon, it would weigh only about 1.67 newtons. Same object, same mass, but much less gravitational force pulling on it.
Okay, so we've got gravity pulling everything together across the universe. Now let's flip the script a bit. What happens when these forces meet surfaces, especially liquids? This feels like shifting gears from Newton to Archimedes.
It is. We're moving from the invisible pull of gravity to more tangible pushes and pressures.
Before we get to the famous eureka moment, we need to talk about thrust and pressure, I think.
Yes, good point. Thrust is simply the force acting perpendicular, or at a right angle, to a surface, like your weight pushing down on the floor.
It's just the force itself. Okay.
But the effect of that thrust really depends on how spread out or concentrated it is. And that's pressure. Pressure is the thrust divided by the area over which it acts.
Pressure, force, area.
Right. So think about why a camel can walk on sand so easily.
Big feet.
Big, flat feet. Its weight, the thrust, is spread over a large area. Large area means low pressure on the sand, so it doesn't sink in too deep.
And the opposite would be something like a very sharp knife, or maybe a stiletto heel.
Perfect examples. Same force from your hand or the person's weight, but concentrated onto a tiny area. Tiny area means enormous pressure. That's why the knife cuts or the heel sinks into soft ground.
Makes sense. And liquids and gases exert pressure too, don't they?
They do, in all directions.
Yeah.
And when you put an object into a fluid, the fluid pushes back up on it. This upward force is called upthrust, or the buoyant force.
Okay, buoyancy. This gets us to that classic puzzle.
Sure.
Why does a tiny iron nail sink like a stone, but a huge, heavy steel ship floats? It seems backward sometimes.
It does seem counterintuitive. But the secret ingredient here is density.
Density, mass volume, right. How much stuff is packed into a certain space.
Exactly. The iron nail, although small, is very dense, much denser than water. So the downward pull of its weight is greater than the upward push of the water's buoyant force. Down it goes.
But the ship, it's made of steel, which is also denser than water.
But the ship isn't solid steel. It's mostly hollow. It encloses a huge volume of air. So its overall density, the total mass of the steel and everything inside, divided by the huge volume it occupies, is actually much less than the density of water.
So the average density is low, even though the materials are heavy.
Right. Because its average density is less than water, the buoyant force from the water it displaces is enough to support its total weight. It floats. It's all about comparing the object's average density to the fluid's density.
Density is king when it comes to floating or sinking. Got it. Which brings us to Archimedes himself. The story involves a bathtub, doesn't it?
The famous story, yes. He was apparently tasked by the king to figure out if a crown was pure gold or if the goldsmith had cheated by mixing in cheaper silver but without damaging the crown.
How could he do that? He needed to know its volume to calculate the density, but the crown was an awkward shape.
Exactly. The legend goes he was getting into his bath, noticed the water level rise and overflow, and suddenly realized, the volume of the water that spilled out must be exactly equal to the volume of the part of his body he'd submerged.
Eureka. He found it.
Apparently so. He realized he could measure the crown's volume by dunking it in water and measuring the volume of water it displaced. That let him calculate its density and check the gold's purity.
But he also realized something deeper about the water pushing back, didn't he? The principle.
Yes, Archimedes' principle. It states that when an object is immersed in a fluid, either fully or partially, it experiences an upward buoyant force. And the magnitude of that force is equal to the weight of the fluid that the object has displaced.
Wow. So the upward push equals the weight of the water pushed out of the way.
Precisely. That's the key. It tells engineers exactly how much water a ship needs to displace to float while carrying its cargo. The weight of that displaced water must equal the total weight of the ship.
That's incredibly useful. And it's not just for ships, is it?
Not at all. It's fundamental for designing submarines, controlling how much water they take in or pump out to control their buoyancy and depth. And also for simpler things, like hydrometers used to measure liquid density, or lactometers that check the density and therefore purity of milk based on how high they float.
So wrapping this all up, what's the big picture here?
Well, we started way out in space, didn't we? With Newton connecting a simple apple to the moon's dance, all governed by the universal pull of gravity. We saw how mass and distance dictate that pull.
Right, the inverse square law and how the moon is always falling but missing.
Then we zoomed back in, looked at free fall, GA, and the crucial difference between unchanging mass and location-dependent weight.
And cleared up why feathers and hammers fall differently in air, but not in a vacuum.
And finally, we dove into fluids with Archimedes. We saw how thrust and pressure work, and how density and the buoyant force, the weight of displaced fluid, determine whether something sinks or floats.
So from the pull of planets to the push of water, you now really have the basic tools to understand so much why we have tides, why massive ships don't sink, even why you feel lighter when you're swimming.
Exactly. It's about understanding these fundamental forces, gravity binding things together, and buoyancy pushing things up in fluids.
Okay, here's a final thought for you to chew on, connecting back to weight. We said weight is mass times g, and g depends on where you are. Now, the Earth isn't a perfect sphere. It actually bulges out a bit at the equator and is slightly flattened at the poles. This means you're actually a tiny bit closer to the Earth's center if you're standing at the North or South Pole compared to the equator.
Okay, slightly closer at the poles.
Which means g, the acceleration due to gravity, is slightly stronger at the poles than at the equator. Just a little bit.
I see where this is going.
So imagine you go to the North Pole and buy exactly 100 kilograms of gold, measured very precisely by its weight there. Then you fly with that same gold, the exact same mass of gold, to the equator.
Where G is slightly weaker.
Right. If your friend meets you at the equator and measures your gold again using the same weight measuring scale, would they agree that you still have exactly 100 kilograms of gold by weight? Something to think about. That difference between constant mass and variable force.